Hey everyone, welcome back to my channel EduVibe. In today's lesson, we are doing some practice questions of the first part of the electromagnetic radiations, which is related to physics. So we were starting from the introduction of the electromagnetic radiation to the Snell's law practice questions, which are very important. So let's start with the from the frequency point of view when we do the frequency in the first topic. So the important topics from that. So first question says that for the source vibration shown below, determine its frequency in vacuum. So if we are given the some vibration source and we have to find the frequency. So to find the frequency from here. So here we have some frequency over there and we have a t microseconds, which means this 8.40 is our time. So it's given us the time over there, so which is 8.40 microseconds, and that time is for some particular frequency, the particular vibration occurring, and we have to find that how many periods can be occurred. So what can I talking about with? So we have to find the t because we know f is equal to 1 upon t. But there is not another way to find this things because we don't have wavelength. So we can't use c is equal to frequency times wavelength. We have just that formula, and in the formula we have that t, which is the period. And period is that at how many number of cycles per unit time can be occurred. So we have to find basically the how many times that vibration can be occurred at the one rotation. So first time they go from here to here, and after that they repeat that, but they repeat this again, one, this one. So they repeat over there one, and then repeat over there two, then at last they again repeat this over there, and at last they go to three. So the total period is 3. So they do the 3 times same vibration, which is that something like the S. So that means that this 3 times they do some same period of time. They're doing the same frequency in each time. So this means we have 3 period, which is equal to the 8.40 microseconds, which is 3t is equal to this. And when we find the t from here, so we get 8.40 microseconds, divide this by 3, you will get about 2.80 microseconds. So from here you will get a t, which is the period, and in seconds. So frequency is equal to 1 upon 2.80. Micro has the value of 10 raised to minus 6 seconds. So you will get, when you solve this, 3.57 into 10 raised to power 5 hertz. So that's how you can find from the diagram frequency. But you have to know that how can we find this? How can we find this t first? Then we have to plug this into this term and you get the frequency. Same case you did with the period when you have to find the period and you have a frequency. So that same case you have to do with that diagram below with that thing. This is a small question you get in the 1 mark. So the tricky part is that this one, that you have to do this first, then you have to find it. So next question. Next question says that a kitchen appliance produces a radiation with a frequency of 2.445 gigahertz. How to classify the type of the electromagnetic radiation and how to find the wavelength of the electromagnetic radiation in a vacuum. So we have that frequency over there, which is 2.45 gigahertz. So which is giga? So giga has the value of that cap big G has the value of 10 raised to power 9. So in your spectrum, in your table of spectrum, so where is that the frequency is 10 raised to power 9. So at the range of 10 raised to power 9 to 10 raised to power 11, you can see you have your microwave over that range. So with that frequency, you have a microwave radiation. So this means the type of electromagnetic radiation we have is a microwave. So that's how you can find that the giga has the value of 10 raised to power 9, and you can find that where that 10 raised to power b lie in your electromagnetic spectrum. So that's how you can find this. So this is microwave. So now you have to find the wavelength of this. To find the wavelength, you know c is equal to frequency times wavelength, and wavelength is equal to c upon frequency. So c is 3.0 10 raised to power 8 meter per second. F you have 2.45 into 10 raised to power 9 hertz. When you solve this, you get this about 0.122 meters in 3 seconds. So you get your wavelength from here, 0.122 meters. So that's the question, repeatedly question you will get in the MCQ, in the numeric, or sometimes in written. So that thing, your spectrum thing you have is very important. You have to know the what is spectrum, that how can we memorize it. We have some mnemonic for this. So that thing you have to know from here. So next question. This question is from the Michelin's type experiment. When we do the that experiment, when they find the speed of the light in a vacuum, which is the 2 point something. So that is a question from here. So let's figure it out. How can we solve this? An n-sided mirror. So the don't given us that the side, which is like we have a-sided mirror, this side that we have n-sided mirror, rotates a minimum frequency of 435.5 Hz for the light to be seen in the telescope. If the distance between the two mirrors is 31.0 kilometers and the major speed of light is 2.7 10 raised by 8 meter per second, so we have to determine the number of sides n. So basically we have to find the n. That thing that which we do with the, like if we have an 8 centimeter with that 1 8 times period, that 8 should not be given to us. That is equal to now n. That n is something else, not always 8, is something like any number, any whole number, any natural number they have. So that n should be fine now. So that thing we have to do, and we have a frequency over there. So this is the frequency, this is our d, this is our speed of light, which is our v, you can say that, and we are finally n. So what steps we have to follow? Let's figure out. So one thing when we're doing the Michelin's type experiment, that when we have the distance, we have to multiply this by 2. And when we have to find the distance at the end, we have to divide the distance by 2. So here we have the distance, we already given the distance. So in that case, we have to multiply this by 2. So delta D is equal to 2 times 31.0 kilometers. So when you solve this, you get about 62.0 kilometers. But we don't want in like in that kilometer thing. We want it in meters, because we do that thing is in meter per second. So we have to be in meter per second. So we have to convert this in meters. So you just multiply this by 10 raised to power 4. So you get something like this. So you get 6.20 10 raised to power 4 meters. And we have to find the delta t from here. So why delta t? Because we have v, we have delta t. We have to do the reverse thing. So firstly, we have to find the delta t. That v is equal to delta d upon delta t. Delta t is equal to delta d upon v. So this is equal to 6.20 10 raised to power 4 meters divided by 2.7 10 raised to power 8 meter per second. This is given to us. And that delta t is equal to the 2.296 into 10 raised to power minus 4 seconds. So that's your time I have found. So that time is given to us now. And one thing more, that when we do the this formula we have, for this n, we do this thing. We do 1 upon n times t, which is equal to delta t. That delta t we have, that t we don't have, that bit t, which is the period. That bit period we find from the frequency. So when we find the period from here, so t goes over there and 1 upon frequency. So 1 upon 435.5 hertz. So when you do this, you will get your t of about 0.002296, which is also in seconds, but this is the period. And now you have to find your this delta t is equal to 1 upon n, which is times the big T. That n is your number of sides on mirror. So we have to find the n. So n can be like this. So n goes over there, and you will get about t upon delta t. So bit is 0.002296. This is in seconds, and this is 2.296 into 10 raised to power minus 4. Seconds can cancel out. You will get n, which is about, you can solve this, you get approximately of 10. So number of sides is 10. So and we get the 10. So not always we get the 8, because you know that it's the mission type experiment use the eight-sided mirror, but this is not always that case. That case when we solve for something else, but when we solve for n, this is not directly that n is equal to 8, and we have to find by this whole concept we learn from the mission type experiment. So that's all we have to do in the this experiment and with the n. So let's move on to the next thing, that is then from the mirrors. We do the curved mirrors and we do ray diagrams. Not actually you have given in your examination the ray diagrams that you have not written in your diploma, but you will get the questions in a MCQ form, because in mathematical analysis and that questions are so hand in hand. They will give you the same questions, they both the topics in one question, and you have to solve for the both. And you have to sometimes make the diagram for your convenience to make the things right for you. The question says, following objects we have, stretch the image and need to find the magnification, attitude, and the type. When a concave mirror with the object beyond C, that we have beyond C, that before C. So here we have to find the image. We have made the image, that's the image. So we will, this is a concave mirror, and we follow the exact same steps as we follow in the, when doing that topic. That three rays we have, the three rays we have to follow. In that way, firstly I will make the ray which is parallel to the principal axis and pass it to a focal length. So for this, I will use my scale. You also have to use your scale for the accurate diagram. So put that over there and make the z line till this, and made this line passing through the focal length. So like this line has to be like this. So if you want, so you can make your arrows for your convenience again, which seems like very good for you. Now I will make another thing with this going past the focal point and then parallel to principal axis, is the opposite of this. So then I will be thinking that this will cut this refracted ray. This refracted ray will cut, and I will make that image from here. So for this, you have to sketch this diagram again, that pass into the focal length, focal point, like this, and they should be go parallel. So this, and this, and you will see, you will get your image over there, which is again inverted image. So make the inverted arrow like this. So this is your image. So what type of magnification do you get? So magnification you get the, what type of diminished you get, because this is kind of a small, like this is the large object and you get the small image. So this is like a diminished one. And what type of attitude you get? You get the inverted. This was the inverted orientation, and the type you get the real, because there's only one case in concave mirror that when we get the, then we get the virtual image, a dotted line. Okay, so otherwise you have a real image. So that's three things you have to find, and that diagram you have to make. That this all thing you have to just know about this, that how can you make this thing actually. Okay, so let's move on to the next one, and this is from now mathematical analysis of the mirrors. So this is very important topic. When we do the lenses in upcoming lessons, you will get more like we do the same things in the lenses, and that is that things we have to follow in that. Okay, so this question, an 11 centimeter high object is placed 7.0 centimeters in front of the concave mirror. The virtual image has the height of 55 centimeter. Determine the radius of the curvature of the mirror. So they mentioned that we have a concave mirror. This is a concave mirror. So this means frequency is greater than 0, which is positive. So frequency you have that should be positive. Then now they mentioned that you have a 11 centimeter high object, which is the height of the object. So which is that HO is given to us, which is 11 centimeter. Placed 7.0 centimeter in front of the concave mirror, which is your distance. So which is DO, which is remains positive. This also remains positive, and the virtual image you get. So this is the special case of concave mirror where you get the virtual image and that has the height of 55 centimeter. So here's that thing. Now you have to follow that HI you have given now. Yeah, HI you have to given now, but there should be positive or negative. So if there's a concave mirror and you get the virtual image, so your HI should be positive. So again, that HI, which is your this one, 55, this should be positive. So all things you have here is positive, and you'll find the radius of curvature, which is R. For radius of curvature, you know that radius of curvature is 2 times the focal point, focal length. So for here, you have to find this focal length. So focal length have to be found. So let's do the things and that to know about the more things. So you have the, for F, you have this formula. You have DO, but you don't have DI. So you have to find a DI from here. So HI upon HO is equal to minus DI upon D. Formula, and this is also equal to magnification, but we don't care about magnification for now. We just care about the DI. Okay, you do the cross multiplication and you get about like minus DIHO is equal to HIDO. That minus DI, it stays over there and you get HO over there. But then minus should also be go over there because DI we want, which is equal to the minus HIDO upon HO, which stays the same the answer when you do like this. You get the answer minus. So DI is equal to minus 55 centimeters. DO is 7.0 centimeters. Divide this by 11 centimeters. You will get DI negative about 35 centimeter. Why negative? Because you have virtual image, and in virtual image you have DI is negative. So you get the negative answer, which is right. Now you have to find the frequency. For frequency, you will get F like this, and this whole thing goes to -1. But DO is equal to DO is 7.0 plus DI is negative 35 centimeters, and this whole goes to -1 because we get in F to the F, 1 upon F to F, the goes -1 over there. When you solve this and when you raise to power -1, you will get 8.75 centimeters. Focal length is also in positive because we have a concave mirror. So you have to double this now over there to find the radius of curvature. When you double this, you get about 7.5, but you want like 2 sidhets, so your R is equal to 18 centimeter. So that 3 things you have to follow. Like for R, you want focal length. For focal length, you want DI. For DI, you have to find this DI first. Then you have to do your another steps to find the R. So that's the way you have to follow when you're solving the questions. So for radius of curvature, I directly find this by that whole thing. That's the important thing you have to follow every time when you're solving the questions, like if you want the accurate answers. So let's move on to the next one. And next one is a very special question because this is not like a question we are doing so far. Now we are doing the question which is like a very diploma style question. So what the question says, an object is placed x centimeter in the front of a concave mirror such that its real image is located 3 centimeter in front of the mirror. If the focal point or focal length of the mirror is 2.5 centimeter, determines the object's distance and the image distance from the mirror. So what you have to find? You have to find the object's distance, but they mention that the place between this, so they given us the DO. DO but is equal to the x. There's not any value, there's a x centimeter. There's a concave mirror, which means f is greater than 0, which is positive. Real image is located 3 centimeter. So this is DI. That 3 centimeter is your DI. And the focal length you have to given, this is the value you have to given, so 2.5 positive. Object distance, which is DO. Images distance, which is DA. So you have to find that x value first. From x value you will get to know about DO, and from DO you will get to know about the DA. So whole thing I have focus is to find the x. So for x we use the mirror formula, this one, and you put the values in, so which is 2.5 centimeters, DO is h centimeters, plus DI is 3h centimeters. So you start solving this. So this is 2.5 centimeters, And when you solve this, you get the common denominator where you multiply this by 3 and this also by 3. So we'll get 3h, which is 3 plus 1. This is centimeter. So now you're just doing the cross multiplication. So this is 4. So 2.5 multiplied by 4, which we get a 10 is equal to 3h. So 10 divided by 3 is equal to h, and you have about 3.3 repeating centimeters, which means your DO is 3.3 centimeters. And for DI, you just put h is equal to 3.3 centimeters in that 3h, and you will get your this answer 9.9 something, which is 10 centimeters. So this is your DO, which is equal to h. This is DI, which is equal to 3h. So just you have to follow the step. You do exactly same thing with the mirror formula, and you get the h value because the h things are given to us, and you get the answer from there. So DODIs can be like this. This is a simple question, not a tricky one, but this like diploma style questions you will get in diplomas, in MCQs, in numeric. So that's all you have to do. Let's move on to the next question. Next question is from the refraction part. The index of refraction for a medium is 2.40. So they're given us the n. The distance light travels through this medium in 7.35 nanoseconds. So they given us the n. So we have to find the distance. So v is equal to d upon t. You have to find the distance, which is v times t. You have t, but you don't have v. So you have to find the v first. So n is equal to c upon v. This is equal to c upon n. C is 3.00 10 raised to power 8 meter per second. N is given to you, which is 2.40. But you get, when you solve this, you get something about 125.00000 set zeros meter per second. So it's a very long answer, and you have to put this in over there. And your time is 7.35 nano, means 10 raised to power minus 9 seconds. You solve this thing, you get 0.918 meter something. And when you solve this, you get 0.91. This is like 9. So as I told you, when you're doing this unit, when you're doing this topic, that you didn't tell about that, directly find the n, directly find the c, directly find the p. They will give you the same thing. Like this is a practice question, and this is that same practice question we do in the example one. So there is a practice you have to do. So in diplomas, you get a one question from here topic for sure. And that's the next topic when we do a refraction, when we do the Snell's law. The Snell law has the like two big formulas. Like two big formulas, if you have like big formulas that will used in the graphical analysis. In that chapter, you have so many graphical analysis questions that we made from that unit. So you have to be sure about that questions, that what kind of questions you get from the graphical analysis. So that's the type of question you get. So this is the last question today we're dealing with, and this is from the Snell's law with the graphical analysis. So how can we deal with the question? Let's start with this. So in an experiment to determine the index of refraction of an unknown medium, a student shines a laser light from air into the unknown medium. By varying the angle of incidence, the student is able to determine how the angle of reflection responds to this change in an unknown medium. The graph of student's results is shown below. Using a graphical analysis, determine the index of reflection of the unknown medium. So one medium is air, which is 1. So one medium is the air, which is your n1, which is 1.00. And the second medium is something unknown medium that we have to find. And we have to find with that graphical analysis. So they mentioned that over there we have a sine of angle of reflection, which is the sine theta 1, and we have a sine theta 2 over there. So both the things, and we have a graph, and we have to find the z things to get the slope. But we don't know what slope is equal to. For the Snell's law, so we have the relationship between the n and the sine theta's values. So we have n2 divided by n1 is equal to sine theta 1 divided by sine theta 2. So the sine theta 2, that will be multiplied with this. So sine theta 2 and 2 is equal to sine theta 1 and 1. But that sine theta 2 should be like in y-axis. So you can see over there, this is our sine theta 2 and this is our sine theta 1. And the sine theta 2 is in your y-axis. So this stays over there. And that n2 goes over there. So sine theta 1 and 1 upon n2. And also the sine theta 1 is your x-axis. So sine theta 2 is equal to, you will like combine this ny upon n2 and it isolate the sine theta 1. So now you are, this is your y, this is your x-axis, this is your slope. So now your slope is equal to n1 upon n2 and you have to find the n2. So n1 upon slope. n1 you know, which is 1.00. So we have to just find the slope to get the answer. For slope, you have y2 minus y1 upon h2 minus h1. So get the two values from here. So we have to find some accurate values from the graph to get to that quotient. So I've put that value first because this is not very accurate graphs, but you get the accurate graphs in your examination, in your diplomas, and this will, in this examinations too, you will get the accurate graphs, but this is not very accurate, so I will make just random point and I will get them some approximate value of like this something 0.150. x1, this is your y1. For next value, I will take from here something. So this is again 0.4060. So if you get any other value from here, if you want to do some another value, you can take that value, but it should be accurate. Not like very accurate, but should be like something accurate. So you have to use that values and put that in this y2 minus y1, which is 0.310 minus 0.5150 divided by 0.460, 0.220. And you get the slope of about 0.6667 something. You have to put this in. So n1 is 1.00 divided by this. Make sure you use the non-rounded value. And when you will find about 1.50. So this is your n2. This is not like you will get like 1.50, 1.52, that all okay values. So that should be the value, but should be a slightly difference in your values too. So that's all things we do when you do the depth analysis. Depth analysis is very important in the unit 2. We use that in the forces and fields. We use that in that unit 2 because we have a lot of formula to cover in this, and we have that exact same things for this too. So that's all thing you have to do, and this is end for this practice question lesson. So in the next lesson, we'll start with the second part of this unit, which is more focused on the dispersion. We do the lenses, we do interference, we do some diffraction type questions, and then the last part we have the model physics. So that's all for this lesson, and we will start the next part, which is a dispersion and the recombination. Very easy topic, and we'll do that topic very soon. And so learn with EduVibe, learn smarter, not harder. Please like, share, and subscribe to my channel. If you have any questions, let me in the comment section. See you in the next lesson. Till then, stay creative with EduVibe.